Welcome to Insight Builder channel, large language model automators, Python experts, and my dear friends. Fine-tuning and inferencing large language models, a definitive guide. Let's dive into the overview. We'll start with a brief understanding of what we are going to do. Next, I will show you a fine-tuned model and the actual model output difference. We'll be looking at that as a demo. And then we will move to the Jupyter notebook and discuss the hands-on. So in case of the hands-on, we will first dive into the tokenizer. By loading the tokenizer, we will look at the various parameters that you can pass to the tokenizer object and see how you can manipulate the text that you are going to work with. We will dive into the operations level of working with the tokenizers. I will not be discussing about the algorithms. I will not be discussing about what is happening in the backend. It's more about how to use the tokenizer objects in transformers libraries. There are other libraries like Keras, JAX, etc. I will be primarily working with transformers, and that too with PyTorch backend. We will be moving to loading the model with and without quantization. So in this video, we will be primarily working on loading the model without quantization, because we will be working with a small model, that is GPT-2. We will also look at how to get the model ready in case if you are working with a very big model. I'll be showing you one of the models that I have trained, the Gemma model, the recent Google Gemma model, using the quantization method. I'll be just going through the notebook, but I'll be diving deep into that notebook in the next video. I'll also introduce something called as data collators and introducing the training args, the trainer, and finally training the model. The concentration will be mainly on tokenizer, training args, trainer, and training the model. So with that said, let me move to the Jupyter notebook. So this Jupyter environment that you are looking at is from my Linux server that I am running, Ubuntu 22.04. You can see that I have already split this window into multiple tabs. So in this area you will see the code, and this area you will see that I'll be showing the graphics card output. So graphics card status. I am running the NVIDIA graphics card with RTX 4070. The driver that I am using is 535.154 and the CUDA version is 12.2, meaning the card is completely updated. If you are using Ubuntu 22.04, then this shouldn't be an issue. You will be able to get it up and running without much of a challenge. If you have any questions on this, installing the driver and if you are facing any problem in getting the driver to work, do leave it in the comment. I will try to make a video on that separately. Here, what you have to observe is this particular memory. You can see that the GPU memory of almost 3.2 GB is getting used out of 12 GB available. And this is the wattage, and the base wattage is 14 watt power consumption. And it's running at 41 degrees Celsius. So understanding and looking at the important parameters of your GPU is very, very important. Right now, the GPU card is running at 41 degrees Celsius, which is pretty cool. And it can go up to 80 to 90 degrees Celsius without much of an issue. In fact, it has never gone to that extent, even if when I am training the model for more than 10 to 12 hours. So graphics card cooling wise, it's really good. With the graphics card discussion out of the way, now let us move to the demo of the model. What I'm going to do right now is this particular code that you're seeing here. I am working on Gemma model. So Google Gemma 2 billion inference tuned model, instruction tuned model. Sorry about that. Also, I would like to show the transformers version that I am following. The transformers version that you need to follow is minimum 14. Excuse me. It has to be minimum 4.38.1. Only in 38.1 the the Gemma tokenizer and the Gemma auto auto model for Causal LM model is loaded. Before that, if you use 3.7, 4.37 or 4.36, this particular model will not get loaded because that class is not defined inside the transformers library. So ensure that you are updating your transformers library before you jump into this particular code. So in order to update the transformers library, you have to just use this inside the inside your Jupyter notebook itself. You can use pip install and capital U's for upgrade, and you can call transformers. This will update your transformers library to the recent one, or you can go to the terminal and run the same thing. I'm not going to do it here because I've already updated it. Moving further, here as you can see that here we are going to load the language model. So we are going to use auto model for Causal LM. In case of transformers, this particular class is going to load the model and place a Causal LM head on top of the model. Anybody who is listening to this particular video, if you don't have the basics of the language model as well as basics of the neural network model itself, then I would suggest to take a look at my other videos that has been posted on the various playlists in my YouTube channel. I have been primarily discussing on the problem solving on missions perspective, where I discuss about the installation of Torch, working with the PyTorch model, even using all these PyTorch model inside the Raspberry Pi. So I have tried to explain everything, especially in this place, PyTorch backpropagation explained. You can understand a lot from this particular video. So do take a look and see how the models are getting created inside the PyTorch. And when you come to this transformers library is abstraction on top of multiple backends like PyTorch, JAX, TensorFlow, Keras, and all these backends. If you don't understand how the backend is working, like how PyTorch models are working, or how the TensorFlow models are working, and how they are getting loaded, this is going to be really tough to understand. I will try to dive into the various complex areas and try to simplify it to make you to wrap your head around what is exactly happening inside the abstraction. However, I would really suggest that try to take a simple PyTorch model, like create a linear model and try to load it and see what happens. This is very, very important. Let's proceed. So here I'm calling Google Gemma 2 billion inference instruction tuned model. And in order for this model to be loaded, you have to go to Hugging Face Hub and you have to first of all accept their Google terms and conditions. Here I've already downloaded the model, so I will not be asked any questions. In case if you already got the terms and conditions accepted, then you need to import from Hugging Face, import notebook login, and then you need to call the notebook login here, and then you need to execute this. So this will actually ask you to give you the token, the API token of Hugging Face Hub, and you need to provide that. After you provide the token, then you can execute this particular cell, or else this particular cell will throw an error telling that you don't have access to Google Gemma 2 billion instruction tuned model. Next comes the config, the quantization config. The model that we are going to look at is a 2 billion model, and I'm going to show you what will happen if I don't use this quantization. So we'll be loading and we will be working with the models at a very low level. So let me go back to the demo. This particular step where I show how the fine-tuned model and actual model differ, this is going to be pretty long, because the interesting point of the model loading and seeing how it actually moves to the GPU memory is very, very important. As you go into training the model, most of the time you will come across something called as out of memory error. This is a very famous error that you guys will start face when you start fine-tuning. Moreover, I am I'm using a 12 GB graphics card. You can actually train a lot of models with lower memory also. With even 8 GB graphics card, you will be able to train. But below that, if you're having 4 GB or something, I would really suggest that use Google collaboratory notebooks, or go for Kaggle notebooks. The Kaggle notebooks, I'll be sharing you the link for this particular notebook. I had trained the Gemma model, fine-tuned the Gemma model on T4 2 GPUs. So this is possible, and they give you 30 hours per week. So that's a 30 hours of GPU training availability for a week. So it's one of the best options that you've got. 2 T4s, meaning it's really good. And it's a 15 GB T4 graphics card. So when it is going to be 2 times, it is going to be 30 GB. So most of your training needs can be met here. But you need to know what happens and how to actually train more efficiently. So that is the intention of this. Also, one of the intention of this video. So initially what I'm going to do is I am going to go to the kernel, and I am going to stop these kernels. So I have inference underscore PEFT, this kernel that you're looking at here, and I have training TF tokenizer, this one, and I have fine-tuning definitive guide, this one. So I'm going to close all these kernels. The moment I close it, you will see that my usage memory actually drops immediately. So in order for you to unload the model from the when you are working on Jupyter Notebook, the best way is to actually completely shut down the kernel. If you even delete the model, if you try to make the model into zeros, it is not going to work. Your NVIDIA graphics card memory will not get released unless you close the kernel. This is one of the important points that I wanted to highlight and show it to you here in parallel. Right, now that I have come to this level, I am going to move to the step of breaking this cell into smaller cells. Okay, so this particular cell is going to only load the tokenizer. This is not going to load the model, because I am going to load the model in multiple fashions, right? So I'm just going to load the tokenizer, and this tokenizer is not going to impact my graphics card. As you can see here, it's not going to impact it. My tokenizer is ready. You can take a look at the tokenizer details right now, and you'll see that the tokenizer has got lots of informations. In fact, the important point I wanted you to look at is the vocab size. One of the major challenges you will face when you are going to train is that if you are going to increase the vocab by mistake, if you add any additional vocabulary, then your training will fail, because the tokenizer has been trained on 256,000 vocabulary words. If you add even a single word more, then your trainer will not be able to recognize it, and it will fail. So this is something that I learned it the hard way. So do not add any additional vocabulary to this vocab notebooks. And let us also look at the vocab itself. So there are lots of if you call this particular vocab attribute, you'll see that a dictionary of words will come out. Dictionary of words along with the index values will come out. So basically, whenever the tokenizer is trying to tokenize your words or your sentences, this vocab dictionary is what is being used. Yeah, it's pretty huge. And understanding how these things are working internally is very, very important. So that's why I'm diving into these things in a very stable and steady fashion. Most of these things you will be actually looking at from the theoretical aspect you would have read about it, but when in the real model, when you dive into the individual components of it, you will learn a lot. So that's the intention of this. Let's go to the tokenizer, and if you look at the max length, so what is a model max length? So if you look at the model max length, you will actually get something gibberish like this. So most of the time, if you're getting a gibberish like this, it is because the model is getting loaded from the local drive. This is something that I've been facing with not just the Gemma model, with various other models also. If you're going to load it from the repository, meaning from the Hugging Face repository or from the Google repository, then you will actually get the exact model length. But here, you're not able to get it. You will not get that. But there is still another way. You can actually look at the config of the config file of the tokenizer itself. So how to look at the config file of the tokenizer? So for that, you will actually have to go to the go back and look at the original file itself, the model file. So where will be the model file in your Linux or in your Windows? If you go to the home in your Linux, in case of Windows, it will be under your users folder, under your username, and inside the username, you will have a folder called .catch. So that's what you need to, that's the folder you need to go into. So I'll go into .catch now. So you'll see that that is inside the catch, there is Hugging Face, and inside the Hugging Face, you will have a hub. And there, if you do an ls, you will see the various models that is available for me. So I have GPT-2, I have Google GPT-2 Tokenizer, and I have Google Gemma. I have to go into Google Gemma right now. So models, Google Gemma. And if I do an ls here, you will see that we are getting a lots of options here. So you have to go into snapshots, and inside the snapshots, there will be many other snapshots also. This is one of the challenges when you come across these kinds of files. So which file to use? Always use the file that is the latest, right? Here it is, the video that I'm making it is on February 24th, and I should use this 9F series data. So I'm going to go to 9F, and if I do an ls here, you'll see that there are lots of files here. So this is the exact place where you can get the details of the models as well as their configurations. So you can see that the config.json, this is the overall model configuration, and you'll have tokeniser config.json, and also there are various other JSON files, and this is the safe tensors. This is the actual model file. So if I do an ls lt, you'll see that you'll see that first of all that this is actually a link file. This is this file is not actually the whatever you are seeing is just a link to the blobs folder, and inside the blobs folder it is linked. So this is how Hugging Face Hub keeps the files. It keeps as links. So this links will not give you a proper understanding of what is the size of it. So you have to go to the blobs folder and take a look at that. Let us do a cat on tokenizer.json. And you'll see that once you do tokenizer.json, the same thing that you got in the vocabulary, you will get it here also, right? So these are the ways you can, try to get hold of the internal workings of the model, internal workings of the various parts of the model. The idea here is to look at the config of the tokenizer, and once you look at the config of the tokenizer, you'll see that it gives a lot of information about the added tokens for the decoder, the various decoders that has been added, and also what are the additional tokens that has been added, like the beginning of the sentence, the end of the sentence, the start of the turn, end of the turn. All these has been updated in this particular configuration, and that is something called as chat template. So any model that is instruction tuned, it has a chat template, and this chat template uses Jinja templating options. If you are not aware of Jinja templating, take a look at the Jinja template library. It looks intimidating, but once you brace yourself and train on couple of there are mainly two different classes in Jinja templating. If you train on that, it is more than sufficient. So take a look at that. You'll actually get it through. And you see the model max length that you're getting is from this place. So that's what I was talking about. So this is the model max length that is coming out, and this is the tokenizer class, the Gemma tokenizer class. If, as I was telling you, if you don't update the transformers to 4.38, this Gemma tokenizer class will not be present and it will throw an error. That's what I was talking about. So a lot of these things you can understand by going through these files. Also, since we are here, I would like to go into the config.json also. This is the config.json of the entire model, and you can see the architecture is Gemma for Causal LM. This particular class or the architecture also has to be updated in the transformers library, and that is updated in 4.38. And you see there are various other parameters that has been used for creating the model. This parameters that you are seeing here is all that you need for building this model. And you can see the vocab size here, 256,000. So this is same as the vocab size that you saw in the tokenizer. And when it comes to the torch D type, the scaling, also the model, Gemma model uses rotary embeddings, and you can see the max position embeddings is 8,192. And we have an hidden size of 2048 and the head dimensions of 256. All these things might be foreign language to you if you're coming into this video just to understand how the fine tuning works. But why I am actually diving into all these things, because I want you to actually go back and look at the basics also a bit before you start fine tuning, right? So as I told you, this particular part I am going to dive into a lot of details and then move on to the next step. So with this said, let us go back to the point where we were discussing the vocab of the tokenizer. As you already saw that we cannot use the tokenizer's max length, we will have to be careful about this. Just keep this in mind. When we go forward, I will explain the same why. Next, I am going to load the model, and this time I am going to load the model with automodel.causal LM from pre-trained, and I am going to load the model using the model ID itself. So I'm going to load the model with model ID, and as you can see here, I am not having any kind of quantization mechanism. And one point I will add here is called as device map auto. If I don't do device map auto, even if I do a device map auto, there is a high probability that the model will get loaded into the CPU only. It will not get loaded into the GPU. So let us see what happens. So I'm going to execute this, and you'll see that it takes a bit of a time. And once that gets processed, and you can see here that my model has got loaded into the GPU. So you can see my memory has increased up to 10.25 GB, and in the bottom you can see that there is an additional line which tells that this particular process ID which is running Python 3 is taking this much amount of space. So this particular file, this particular output from NVDIA-smi is very, very informative. And if you don't use device map auto, so what I'm going to do is, as I told you, I'm going to stop this kernel, and the moment I stop this kernel, it will move, the memory will get released. Again, I'm going to do this model loading, but this time I'm going to go to this place and I'm going to run htop. So htop is another application in Linux. If it is not available in your Ubuntu or in your Fedora, try to install it using the respective installers. You have to call the htop installation. So here I am having 32 GB of RAM, and around less than 1 GB of RAM is getting used. So that's why I like Linux and Ubuntu for that matter. So it's using less than 1 GB. And what I'm going to do is I'm not going to have this device map equal to auto. So let us see what happens in this case. So I'm going to reload the model. I have to do the things again. So I have to start the kernel. So you can see the kernel is getting started. The kernel is getting started. And then the tokenizer is loaded. You can see the loading of the tokenizer itself is taking some additional memory, and I'm going to load the model. This time when I load the model again, so the model has loaded, and you can see that my memory of around 11.2 GB is getting used. One good thing about Kaggle notebooks is that you can see that entire loading of the RAM and loading of GPU directly. But if you are not going to use Kaggle, if you want to do the same thing in your local machine, then this is how you look at it. So the difference is that if you use device map equal to auto, and if you have a GPU graphics card, the model will get loaded directly onto your GPU graphics card itself. But okay, now that I have mistakenly loaded this into my RAM, how to move this model to to GPU. So it's very simple. You have to call the to method and you have to send it to CUDA. That is all you have to do. So if you are having single GPU graphics card, then doing this will actually move to CUDA. You can see this here that I have moved to CUDA, right? So it is as simple as that. So I have moved the model from the RAM to CUDA. So the 11 GB of RAM that was available was completely freed out. So yeah, a couple of residual memory is getting used here, but most of the entire model moved from the RAM to the graphics card memory. Yeah, that is how it works. And you can actually move the entire 11 GB of data in matter of seconds. Again, keep this in mind. The GPU can only do the operations at with the memory that is already loaded. It cannot actually take anything from your RAM, or it cannot take anything from your local hard disk. You have to feed the GPU RAM with the data and with the instructions that you want it to process, or else it cannot process. So this is one of the things that I like about GPU. People who are new can really get tripped up in this particular area. Okay, moving forward. So we have seen an entire process on how to actually load the model, and we have not even crossed the first step. We have not even crossed how the inference works, right? Yeah, that's one of the interesting points of understanding how the large language models works. Let me continue. So what I'm going to do next is I am going to continue the inference process. I am not going to quantize the model right now. So I'm going to continue the inference process. I'm going to move this a little up so that I don't need to use this CUDA anymore. What you can do is, just a minute. Yeah, that should be here. So you can I'm just changing a couple of parts of the code so that it will be easier for you guys to understand. Yeah, so here you can see that I'm importing torch and I'm checking whether the torch is able to find a CUDA device, and if it is able to find the CUDA device, then I'm going to make the device as CUDA. So instead of this CUDA mentioning here, you can actually say it as device. So that is one of the things that most of the notebooks you will find. And here I'm not going to execute this. I'll execute that cell later. Here, this particular function is going to do a couple of things. So this function is going to tokenize the input, that is the prompt that you are going to provide, and it is going to return it as tensors. Second, it is also going to take the model that you have already loaded. So we have loaded a model, Gemma model, onto our GPU. It is going to take that also. And third, once that model is loaded, it is going to use that to generate based on the input IDs that the tokenizer provides. And this input IDs has to be moved to the device. This is important. If your input IDs are not moved to the device, then it will throw an error, because the model is inside your GPU, but the input IDs by default will be in your RAM. So how is the RAM going to tell to the GPU that use this input IDs? It cannot. So the RAM has to move the input IDs to the device. So this is how it is being done. And then the max token output that we want is 50. And finally, we are going to decode it. So all these things, we are going to do it inside this particular function. And I'm going to make this little more easier by breaking it out. So anyway, I'm going to execute this first. I'm going to show you how the model output is. I need to execute that first and then execute this. So it will take a second. You'll see that model is getting executed here. From 10 GB, it became 11.3 GB. So this is one more thing that I want you to understand. So whenever the model is going to process your input, it is going to take additional GPU RAM also. And this is one of the reasons why you might actually end up with out of memory error. You see, I have got 12 GB of RAM and almost 11.3 GB of RAM is used. And in case if I actually increase this size, if I make this output tokens to say 2000, I can do that. I can actually do it to any level, right? And once I do that, you'll see that the model has to process it. And in order to process it, in this case, it did not take a lot of RAM. But if you're going to do it continuously, and if the model is already consuming around 12 GB, then it will actually become out of memory. This is one of the ways that you will face out of memory error. And you can see that it is actually giving me the output, which is a little more bigger also. Let me reduce this, because we are going to use the same function for another one option also. So this is how the inference happens on the pre-trained model. So we take a natural language, we tokenize it. So I have not dove into Tokenizer yet. I am just going to execute, tell you the process. We'll be diving into the Tokenizer in a couple of minutes. Then we have the pre-trained model, that is the Gemma model that we discussed right now. So what is a pre-trained model? A model that is already trained on a huge corpus of data is called a pre-trained model. A model is, once the model is trained, its weights are modified for based on the data set that has been pushed into it. So that is called a pre-trained model. And this language model takes the tokenizer input, it does the processing, generates the output, and gives it back to the tokenizer. The tokenizer decodes it, and we get an output. So that is what has happened here. The prompt came in, the tokenizer tokenized it, moved it to the created the tensors, and here it moved the tensors to the GPU. It used this method generate to generate the output, and it sent to the tokenizer using decode, and it decoded the output. So all this is what happened, and we got this output, and it's good. So we asked what is sunshine recession, and it started discussing about some economic crisis. Fine. So this is one thing. But apart from this, I already have a model that has been trained. I have a Gemma model that I trained recently for almost 720 steps. And you can go here, and I'm going to go to the place where I have stored the training files. So I have stored it in this location. So I have a Gemma minimal folder, and inside the Gemma minimal folder, I have the checkpoint 720. So this particular folder contains a fine-tuned PEFT adapter. It is not a complete model. It's a fine-tuned adapter which is loaded on top of the model that I have here. Sorry, that I have in this location. Yeah, in this location. So this is a plain model that has been given to me, and I have not done any kind of quantization. I have not done any modification here. So it's a plain model that I'm having, and this is going to actually most probably create a out of memory. So let us see what happens when I try to load the adapter on top of the regular model. So because you need to first of all face the problem before you solve the problem. Most of the classes in Python, the methods in Python have been created for solving a problem. But when you are actually going through the tutorials, when you are working with the various blogs or various videos, they actually don't discuss about the problems that these particular methods and classes solve. They directly introduce those classes. In my case, I prefer to first of all share the problems and then tell how to solve the problems using the various abstractions. So now the problem that I'm having is that I have a adapter, that is a PEFT adapter that has been trained, and I want to load that adapter on top of my model. And for that, there is a separate library called as PEFT that you need to install. I'll be discussing that separately in a couple of minutes if it is possible, or else in the next video. Let us try to load this model. I'm going to import this PEFT class from PEFT module, and I'm going to use PEFT from pre-trained, and I'm going to point that to checkpoint 720. So let us actually go to checkpoint 720 and see what is the size of it. checkpoint 720, and let us do an LSLTRH. Okay, so this particular adapter safe tensor is coming around 2 GB. You can see that here, right? It's coming around 2 GB, and also you can see that there is something called as optimizer.pt, and this optimizer.pt is 4 GB, and this optimizer is used only when you are doing your training, so you don't need to worry about when you are inferencing. Okay, and apart from that, you can see that the various tokenizers and the adapter configurations also here. So let us actually open the adapter configuration. Adapter configuration, and you'll see the adapter configuration that I have used in this particular training, and I have worked on these target modules, and I've used the LoRa option. So I'll be explaining these things separately, but I want you to see that these are the things that is implemented already. Let us try to load right now. So I am trying to load this checkpoint, and let us see what happens to this particular process. I'm going to load this. Once I execute this, you will immediately see that I'm getting an out of memory error, because already I was having almost 11.3 GB of GPU memory already used, and if I load a 2 GB adapter on top of that 11.3 GB, it will cross the available space and it will fail. So you see that CUDA went out of memory and it tried to allocate 1.95 GB. So this is the level of understanding one must have if you have to work with the transformers model, work on PEFT or bits and bytes quantization training. If this level of knowledge is not there, you will actually face a lot of challenges, and you will actually stumble a lot. That is one of the points that I am going this deep. Now that you have seen the problem, I'm going to close this kernel, and now we are going to load the model in a different way, right? So what we are going to do is we are going to again start the kernel, and we are not going to run this particular line. So here we are not going to run this line. So let me actually add device map equal to auto. I'm not going to run this line. I'm going to go down, and I'm going to remove this. I'm going to execute this. So this is a second execution, and then I'm going to use the bits and bytes configuration to load the model in 4-bit. So I'm going to compress the model this time. Instead of loading it in 10 GB of space, I'm going to load it at, you look at it. So let us see how much is the space that is going to consume. I'm going to execute this cell, and you can take a look at the GPU memory. It's 22 MB right now. So once I complete this particular load, you'll see that it is taking just less than 2 GB. Yeah, the model that was consuming almost 10 GB has been compressed to almost 2.8 GB. How is this possible? Because the model parameters, 2 billion parameters, was initially at 16-bit of memory space was being consumed, but now it is only consuming half a byte, that is 4-bit. So that's why it is almost 1/4. So that's what you are seeing here. So from 2 byte, it is half a byte. So that's 1/4, right? Okay, once the model is loaded, I'm going to execute this particular function because we need this, but I'm not going to execute this right now. So if you want, you can execute this. It's not going to hinder your progress. Once you execute this, it will again load a bit of, take a bit of GPU memory, and it will give you the output. So you see that the output is not modified. And now I'm going to load the PEFT model. And when I load the PEFT model right now, you'll see it is taking around 6 GB. So from 3.4, it became 6.8. So almost 2.4 GB of additional space has been used. And then once you execute the trained model output, you'll see that the trained model is giving me the output here. So also you can see that in case of the trained model, I'm getting a completely different output. The phrase "a case of books" is a tongue twister. I'm asking about what is a sunshine recession, but it is talking about something altogether different. Why this is happening? Because the Gemma model has been fine-tuned for 720 steps using a Dolly dataset. So I'll be sharing. You can actually look at that in this particular notebook. I'll be sharing you this link also. You can see what has happened here. Okay, that's a different point altogether for a different video. You saw how the challenges we are facing and how the inference is happening, and this particular process, how to use the pre-trained model to do the inferencing, and then how to use a fine-tuned model that has used the PEFT adapters and then load it. So if you are not going to use a fine-tuned model with PEFT adapters, you can load the model directly. That is what you are going to see next. So this is I hope that till this video you have learned a lot of stuff. So let us do a recap. We initially started with a brief overview, and we started to understand how the model is getting loaded. We also looked at how the transformers libraries and what kind of libraries you need to update in order to get the auto model for Causal LM to work properly. And we dove into the model details by looking at the config files inside the Linux environment. We looked into the NVdia-smi output details, like what are the various parameters you need to look at it, the memory, the power, the temperature, etc. Then we moved to the tokenizer. We looked at the various parameters inside the tokenizers. Then we looked at how to load the model, and we saw how the model loading can impact the memory usage. And we moved further. We looked at how the model inferencing happens. This particular process of converting the text to tokenized data and convert it back to the text after the model processes it. We looked at that. Then we moved to understand how to load the PEFT adapters, and we saw the challenges. If your adapter is around 2 GB of size, and if you're going to load it in a model that is already taking almost 11 GB of VRAM, and we load 2 GB more, it will create a out of memory error in CUDA. So we moved back and we started to use the bits and bytes quantization process. And once we use the bits and bytes, the memory used by the model, the original model, is very low, almost 1/4. And then we loaded the PEFT model, and then we did the inferencing. So this is what we have done till now. But the video title says that we are going to fine tune a model. It's not just inferencing. Fine tuning is the primary objective. And to do the inferencing itself, we learned a lot. For last 45 minutes, in order to do the inferencing, in order to load the model, in order to manage the memory that you are having, we had to learn a lot of stuff. And important point is that once you are looking at this video, I would suggest that you take your own notebook and you start processing. You need to start practicing the various moves that I communicated in this video. The more you are comfortable with moving the memory or moving the data from your RAM to your GPU back to the RAM, completely deleting the memory, restarting the kernel, all these things you have to be very, very fluent with. That's how you can learn really fast. Now we can move to the fine-tuning process. So what you are going to do in the fine-tuning process. So before we move to the fine-tuning, a definitive guide, this particular fine-tuning model we are going to use is GPT-2, and we are going to we don't need to use LoRa adapters here. We don't actually need to quantize the model, quantize the GPT-2 model, because it's very small. You don't need to quantize it. If you have even a 4 GB graphics, I think 8 GB graphics card, you will be able to fine tune it without any challenge, but 4 GB will be a challenge. So let us see what will happen if you are having only 4 GB graphics card. And before we dive into this particular notebook, I want to go down and I want to explain the fine-tuning process or the training process. So in case of the training process, what happens is that you take a natural language data set. So in this case, it's NatLang sentence, but in this case, it's the entire data set. Most of the time, the data set is either a list of dictionaries, and that dictionary has been converted into a kind of a object which you can do a lot of other stuff on. I'm not diving into the dataset class. You can take a look at the videos that I've already uploaded in my YouTube channel. You can look at the playlist where I have completely given a lot of information on transformers library. So there you can look at that. Then we have the tokenizer padding and forming process. This is called as pre-processing. So I'll be showing you what this exactly is in the notebook. That will be better. And then we'll use the trainer. In case of transformers, there is something called as trainer, where you feed the trainer with the processed dataset, train and test dataset, and you feed the language model, and you actually have to enable the train mode. I'll be explaining you how that is done, and then you will have to give an optimizer also. This optimizer is the teacher. So it tells the model that your output is little bit off or little bit different from the required target, and it teaches the model back. So this optimizer is very, very important. As I was showing you in this particular area, this particular part, it's taking around 4 GB of space, right? So this optimizer is the teacher, and this evaluation process is where the loss is calculated. So you can take a look at this entire process here. So the training process, each data point in the dataset is moved into the language model. The model generates the output, compares to the labels, calculates the loss, updates the model parameters. So this updating the model parameters is done by this optimizer, right? And all these things are completely abstracted. PyTorch, on top of it transformers, and you don't know what is going to come after transformers. Yeah, believe me, already there is one more library called as Transformers Reinforcement Learning, or TRL. The TRL library can provide you multiple types of trainers. It is called as SFTT trainers, or supervised fine-tuning trainers, reward model trainers, and DPO trainers, PPO trainers. All these are making it much more difficult for people who are coming new to the large language models to learn about what is happening at the base level. At the base level, this is what is happening. And if you are not aware of this entire process, and if you are going to work only with the trainer that is provided by the Hugging Face transformers, or by any of the other fine-tuning services that is out there, you are going to lose out on this entire basics. And if you are going to lose out on the entire basics, then you will not be able to use something that is available with you. You might have a very good processor or a graphics card with you. You might have been using it for gaming for last couple of years, and now you can actually you might be able to use that graphics card for training, and in fact, making money out of it. So why to lose that opportunity? So that is the primary intention of showing you all these things, and making you as well as your investment that you already have done into something more productive. Let's move forward. What are we going to do in this fine-tuning process? So from now on, we are going to start the fine-tuning discussion. You can actually do these installations if you want. So these are the various installations that you have to complete in your virtual environment. Preferably use a virtual environment. In my case, I am already running in a virtual environment called as AI machine. If I do an ls, you will see that I have a virtual machine environment called as AI machine, and inside this AI machine, I can activate this virtual environment. So you can see this is actually a Python installation. Okay. Moving forward, I'm using 4.38 transformers, and I'm going to start. Let me close this particular kernel. So it is taking 6 GB. So let me close this kernel, and my RAM usage will become 0, almost 0. And I'm going to start this particular fine-tuning definitive guide notebook. So you see it's 4.38, and I'm going to load the classes auto tokenizer, auto model for Causal LM, and bits and bytes. Bits and bytes is not necessary because I'm going to use GPT-2. I am using the notebook that I have created here. So that's why you see that I am also having the bits and bytes here. I'm going to use the model ID GPT-2. This GPT-2 model is already available for everybody. You don't need to sign in. You don't need to do notebook login here. It will be available by default, and I'm going to load the tokenizer. So once I load the tokenizer, you can actually look at the tokenizer details here. Tokenizer, and if I do a model max length, so this GPT-2, the model max length is 1024. So you can go up to 1024 context length. That's what it is saying. And I can load the model GPT-2 model, and you can see that I'm using GP device map equal to auto. And once I do this device map equal to auto, the model gets loaded here. So it's a very small model. It's just taking around 700 MB of data. And do not add any special tokens. So this is one of the major mistakes that I made when I started training the models. If you add any special tokens, this is going to throw an error. In fact, I'll be showing you a cryptic error that it throws, but let me complete this entire discussion, and then I will show the error. And it can take a lot of time out of you. And when you're training, when you're trying to learn these things, and if an error which is cryptic hits, it's going to be very difficult for you to find out how to come out of it. But I will try maximum level to show you the various errors and how to come out of it. And okay, let's continue. So here I'm going to first use the same function to test the model, to test the basic model that you have got. This is not required. And I am asking, give me top 15 golf equipment company names. So this is what I'm asking to the model, and this is the model name. You can see that here. This is the model name, and I am going to execute this, and you can see that it is taking around another 50 MB extra, and it is giving me, and it is not giving me anything useful, right? It's repeating the same thing again and again, but nothing good is coming out, right? I'm going to go through the list. It's repeating. Now what we are going to do is we are going to train the model. And we are going to train the model on this particular data. Let me open the data. And thanks to one of the Kaggle contributors, I was able to use this data, Databricks Dolly. I'll be using this particular data set directly. And when I was testing this Gemma model, I came across one of the notebooks where I saw this data. And that is how I am starting to use this data set. And do give a thumbs up to this dataset in Kaggle so that others can find this dataset and also use it. And you can see that it can be used for training LLMs. It can be used for synthetic data generation and data augmentation. So these are the various purposes of this data. Do take a look. Let us move forward. And this data has got around 15,000 items, and you can take a look at the item. So this dataset has got instructions, context, response, and category. All these things are there, and there are various categories also. So there is classification, there is closed QA. You can take a look at this. There is general QA. All these things you can do, but we are not going to worry about the category. We are not going to worry about the context. What we are going to do is we are going to work with the instruction as well as the response. That is all we are going to do, because we are going to train a causal language model. We are not going to train any other type of task. There are lots of tasks, like we can do classification, we can do token classification, we can work with summarization. No, none of these things we are going to try right now. We are going to simply work on causal language model. What is a causal language model? I am not going to dive into the theory. I am being very frank here, because even if I dive into the theory, lots of people discuss this, but simple answer is that causal language model takes a couple of numbers and it tries to provide a couple of numbers back. That is all. And the numbers that are coming out. So let me go back here. Let me scroll down. You see, I have actually, I have given a numbers here, 1257, 5762, 85565. I have given a list of numbers, and I am getting a list of numbers out. This list of numbers that has come out is from a probability distribution. That is all. And this probability distribution has been created by this particular language model when it got trained. This is a very, very top level overview. This particular language model is made of numbers also. Again, this particular language model is made of numbers, which is created into a form of matrix, and that numbers are modified by these numbers and to get these numbers. This is confusing, right? You might be wondering that how just numbers can create such good looking sentences. You saw that the output was good, right? There was nothing wrong with this output. The phrase "a case of books" is a tongue twister. It's a double entendre. It can't refer to a bad investment, a bad real estate deal, or a bad horoscope. All these things looks like a very good sentence. This is happening because after the model is giving the output, the decoder, the tokenizer.decode, there are various ways to decode the output. This is what is actually helping to do that. So before I actually dive into the fine-tuning definitive guide, I want you guys to review this particular notebook. So this particular notebook actually gives you a lot of information on the tokenizers. Training TF tokenizer, that is transformers tokenizers. This introduces to you how the tokenizers work, in fact, and it goes into the details of the same GPT-2 tokenizer. And you can see that individual examples have been taken. Each of the ideas that I already explained to you has been shared here. And you can see that once you tokenize a particular text, you can see the output here. So this is how the tokenizer is giving the output. And along with that, there is something called as attention mask. Moving forward, you can see that the various steps we have done, and we can load the tokenizer. Apart from this, this particular notebook will also tell you how to train new tokenizers. Whenever a new model like a Gemma or GPT-2, GPT 3.5, GPT-4 or Sora model, even the diffusion models have their own kind of background processors or tokenizers, which has to link with a particular pixel. So these kinds of tokenizers have to be trained. And this particular notebook, I'm not going to go into this notebook in detail. I really want you guys to look at this particular notebook. And this notebook, I have taken it from the tutorials that has been provided in Transformers library. This is not something that I have come across. This is already provided. I have just reiterated it here. And as I was telling you, the more and more complex and easier abstractions are coming out into the ecosystem, these things are forgotten. And people who are coming new to this field, they find it really, really difficult. There are lots of data, lots of tutorials that has been created in the past, which gets completely foreshadowed by the new tutorials. That is the reason, one of the reasons why I'm diving way back and trying to provide you this information. The links for those tutorials will be shared in the YouTube description. So do take a look and try to work on the tutorials manually. All these things that you see here, it was typed. I had typed it and I tried to understand each and every step. Do not copy paste or do not run the tutorials directly. Running the tutorials directly on the Google Colab notebook is good if you are just trying to look at the output. But if you really want to learn each and every abstraction, each and every class, I would suggest that you should type the code and execute it. Do not run directly on the Colab notebook. Even though it is easy, it's direct, do not do that. Okay, fine. We were discussing about this particular area of the dataset, and I showed you the dataset, and I also discussed with you what we are going to use. So we are going to use the instruction, and we are going to use the response. Rest of the things we are not going to care. So this particular cell is going to process that, and let me execute this cell. So I'm going to execute this cell, and the data will contain, let me go down. So the data will contain the instruction and the response. So that is how the output will come. So let me actually show you another one example. So this will be a single line. So let me actually show you a couple of outputs. So this will be a list of instructions and response. and this instructions and response is what we are going to feed to the model. But what we are going to do here is that we are going to curtail the instructions and response to less than 500 token length, meaning the length of the entire instruction and response together should be less than 500 characters. So that's what we are trying to do. Why? Because we want to send to the model a smaller data so that our training speed can be faster, because you are learning. You don't want to work with the huge data or long sentences when you are trying to figure out something. You don't want to sit hours together to find out that whatever you have done is wrong. Doesn't work that way. You have to work on something small, something snappy to get the things moving. Even because you have Kaggle environment, you can do this in no time. T4 will be a little bit slower compared to RTX 470, because the T4 is the T4 GPU is on Turing architecture, while the RTX recent 4070 is on Ada Lovelace architecture. So the architecture is different. If you are having 4090 Ti, it's much better. The speed is really high in that case. Anyway, now that I have given you the background of that, and here, after I reduce the content, I am further reducing the dataset to just 300 datasets. So there are almost 7,339 data points. Out of that, I am going to only take 300 data points. I am going to use very, very less number of data to train my model, and you will see that it still works, but the number of epochs that I'm going to use is little more higher. Let me move forward and I will explain to you what I'm going to do. So this I'm not diving into the various dataset related classes or dataset related methods and functions. Kindly take a look at the separate video on that. It is already there in the playlists. So here I'm going to create the dataset. Excuse me. I need to execute this cell and come back here and execute this cell. So the dataset has been created. Now I am going to tokenize this dataset like this. I have to convert it like this. Apart from converting it to like this, I have to truncate and I have to pad the output to 512. I need to ensure that when I am sending the model for training, so let us go down here. When I am sending this pre-processed output from this dataset, when I am pre-processing and sending it to the language model, all the data points should be of same length. If the dataset point is of different length, your trainer will throw an error. That is where the data collator comes into picture. So there is something called as data collators in Transformers library. It helps in padding. But sometimes when you are trying to work with different data sets from your blog post or from your tutorial, and if you try to work on a different data set of your own, then it will throw an error. You will not be able to understand what mistake has happened. So in order to avoid all that ruckus, manually try to pad the tokenized output to a particular max length. Okay, all this points, the padding, the truncation, max length, etc., is discussed in the TF tokenizer. Take a look at that. And also there is one more resource that I want to share. So this particular Hugging Face space called as Transformers Universe introduces the various NLP tasks structured by topics, and you can take a look at that. You'll find a lot of information regarding the various tasks, also of various domains of AI. If you click on NLP, the entire details of the models that comes in NLP will get updated. You can see that there are various models like encoder, decoder, encoder, decoder model, and inside, if you see what are the various existing neural networks that has been created on this model is also updated. So this is one of the places where you can start, and moving down you'll see a deeper discussion on the tokenizer algorithms. So there are various kinds of tokenizer algorithms, and the various tokenizers that are using that algorithms is also discussed. This is also one of the point I wanted to discuss with you. And then comes the tokenizer options. As I was telling you, the tokenizer has three main options. There is padding, truncation, and max length. And how these things are going to modify is shown below. So there are various trials that has been done, and if you are going to look at this particular output, so you can see that I am just giving the tokenizer with sentence 1 and sentence 2. So this is how the output is coming, and once I am using padding equal to true, you can see that it is getting padded here. You can see the numbers here, so it is getting padded. And if I am going to use kind of padding equal to true with max length equal to 15, and it is actually getting padded up to 15. So, and again, if you scroll down, I have explained it with truncation equal to true, it will truncate with the particular length. So all these things have been explained here, and you can take a look. Then comes the model architectures itself. So there are, as I was telling you, there are lots of NLP tasks, and each of the tasks contains various architectures that can support. So if you, for an example, click on Causal LM, it will update the page, and you can see the various models that are part of the Causal LM. So you can, I have initially given only 4 models, 4 architectures, but if you can extend this, you'll see the various other architectures that is present. And if you scroll down, you will see the class that you need to load, and also the dataset that it has been initially used for training. And also the model used usually is digital GPT. So these are the things that you can see. If you go to translation for an example, so the architecture will again change, and you can see that Opus Books is one of the dataset that you can use for training. The model uses T5 small. The class is auto model for sequence to sequence LM. This is the one of the important resource. I'll be sharing the link also with you guys in the description. Moving forward, so the idea here is the reason why we went there to discuss is that when you're going to do the pre-processing, you should actually send the pre-processed sentences to the to the model in a proper truncated and the same length dataset. If you're going to modify the input ID's length, then it is going to create a problem. Let us go here and I will show you. So I have tokenized, I have done this particular mapping and I have tokenized it. And I am also splitting the dataset, this tokenized dataset, into train and test here. Excuse me, I think I have missed this step. Executing this later, and following that with this. And then you will see that I have a train dataset with 240 data points and a test dataset with 60 data points. It's a very small dataset, right? But you will see it is going to create a difference. And this is what I was talking about, the input IDs. So let me first of all show you the data itself so that you can see what is happening. I want you to follow similar kind of a process when you are doing this tutorial on your notebook. So you can see the input IDs here, and if you scroll down, you will see the padding. So this has been padded, and it has been padded up to 512 12 index. So that is how it has been padded. And let me scroll down. It's all right to scroll down for this particular, and you can see after the 512, you'll see the attention mask also getting padded, and the attention mask which contains the input IDs of the sentence, excuse me, the attention mask is 1 for the input IDs that are the data that is coming from the sentences. Okay, it's coming from the data point, but whichever is padded, so from wherever the padding is starting, the attention mask is set to 0. Basically, we are telling to the model that ignore these padding, and that is how we are pushing it to the model. And once you scroll down further, the same input IDs are copied to the labels also. So we are actually creating a causal language model which is modeling the entire language itself. Okay, we are not giving a particular sequence and trying to translate it, or we are not giving a particular sequence and trying to summarize it. We are not having a target sequence. We are telling that the target as well as the input are both same. You have to learn from that particular target as well as from the output label that you are providing. Both of these things you have to learn. and you have to then try to create a generation output and see how close it is to the output labels. So that is what we are trying to ask the model to learn here. If whatever I told is a little bit confusing, and you have to do it and see. The point here is that learning the causal language model theory is one part. So in the same repository where I am going to share this share these notebooks, you will also find various other tutorials that has been provided by Transformers library documentation, which explains about the ways of training the. Just a minute. Yeah, you can see this particular updates that I'm giving here. These are the various tutorials that is already there in this particular folder in Learning HF Philosophy. It has got all the tutorials. I have updated that. I have typed it out and I have tested it out to ensure that my understanding is accurate. Excuse me. Okay, now that background is done, let us move forward. And if I look at the length of this particular input IDs, it will be 512. Whether it is the sentence data point 10 or whether it is data point 210, the output of the input IDs will be 512. And the same way, output of the labels also will be 512. So the trainer is getting the same length of the data points. It is not getting more or it is not getting less. If this is going to be 512 in one place, and if it is going to be 500 or 10 in some cases, then what will happen is the model will not be able to train. It will actually throw an error. PyTorch will not be able to push the data point through the model and bring it out. So let us go here. As I was explaining to you, that each data point will be pushed into the language model. This data point has to be of same dimension, or else it will not be able to push. I am not going into the PyTorch level and discussing the shape, discussing the views, discussing the reshape, squeeze, unsqueeze, all these methods. There is a separate video on that. You can take a look at it. But in this particular discussion, we are already at a higher level of abstraction. We are abstracting the entire training process. This entire process has been abstracted, and that is why I am trying to dive a little bit deeper, but not really going to a base level. So here you can see it is 762 MB, and if I do a get memory footprint, you will see it is only 475 MB. So why it is different? This is different because that 762 MB has come up after we did some kind of inferencing. So this and the memory footprint can be different. So don't worry about that. And also this memory footprint is the exact footprint of the model weights, not whatever you are seeing here. So it is still different. So keep that in mind. And this steps per epoch is based on the batches. So we have 300 data points. We have split it into 240 and 60. And each batch that we are going to send into the model is going to be 8 data points. So we are going to send, let us go to the dataset. We are going to send 1, 2, 7. So all this data points together, we are going to send as one batch into the model for training. So that is called as per device train batch size. So this is the training arguments that you are going to use. So training argument is a class inside the transformers, which is going to provide the various training setup to the model. And evaluation also, we are going to send 8 data points. We are going to evaluate for each step. Okay, not for each step. We are going to evaluate for 100 steps. So this 30 steps that you are seeing, steps per epoch. So that is how we are going to evaluate. So I'll be showing it to you in action in a couple of minutes. We are going to save for every epoch, and we are going to train for 5 epochs. That is one of the points I wanted to highlight. I'm going to say QLoRa. This is not going to be QLoRa because this is going to be just GPT. I'm going to change this, and I'm going to save this model in my home training, and in that I'm going to store it as GPT minimal. And then this is the place where the model checkpoints will get outputted. We are not going to push the model to the hub, and we are not going to report any of the validation or the training results to VanDB or TensorBoard. We are not going to do that. This is one of the points that I usually face problem with. If you are going to say VanDB reporting, then you need to have VanDB account, and you need to have that API, you need to give that connection, all those stuff. But when you are trying to learn, you don't need that. Just use report equal to none and don't push it to the hub. Until unless it's required, you don't need to push it. But after you are confident that model is really good, then finally when you are going to push the model to the hub, that time you can use it as true. You can give the proper repo ID here and it will work. So lot of discussion on that is already available in various videos. You can use that. But as of now, remove all these things and only concentrate on these ideas. The LR scheduler, the learning rate is important. You don't need to worry about the group by length. You don't need to worry about the LR scheduler. All these things are taken care by default. And one more important point, you might be wondering, we are not giving the optimizer. The optimizer is by default taken up by the training arguments. You don't need to worry about the optimizer. Okay, once you are going to go a little more deeper by using PEFT or using quantized model, that time you need to worry about it. But as of now, when you're going to use the training arguments, you don't need to think about the optimizer. And then the data collator. So most of the time you will see this data collator for language modeling. This is required because you need to send this data collator in the trainer. And also you need to send the tokenizer also along with the trainer. So you need to send the model, you need to send the tokenizer, you need to send the data collator, the train and the evaluation dataset. So the train and the test dataset that we created, 240 data points and 60 data points, you need to send that also. After that, you need to send the training args. Yeah, don't forget this. Most of the time I used to forget this, so don't do that. And once you have sent all these things, execute that and then finally come and click on train. So once you start training, you'll see that 700, it was using 700 MB, but now it is using almost 11 GB for training. So what is happening here? This is one of the reason why I was using a very small model. Initially, I was telling you the GPT-2 model is very small, right? The reason why I was using a small 700 MB model is that when you're going to train with the regular optimizer, it is going to take a huge amount of data. And also, a second thing that you'll see is that we are training with a batch size of 8. Just a second. So here the batch size is 8 and we are training, and it's really, it's blazingly fast, right? But for a moment, if you don't have 12 GB of GPU, then what are you going to do? Is there a better way? Actually, there is a better way. So that's what we are going to see next. Let us, the training has happened, but let me complete this entire process so that you guys can see the output and then we can proceed further. And we are going to load the checkpoint. I think checkpoint 150 will be there. Yeah, checkpoint 150 is there. The training checkpoint I'm going to load, and I'm going to load the trained model. And keep one thing in mind. So right now, after the training, the GPU has been removed. The optimizer from the GPU has been removed, and you have 3.25 GB. So now it's not going to be a problem. You need to move the model, the trained model, to the GPU. So you see that it is, again, it increased here. I have moved it to the, I have already moved it because it's auto here, so you don't need to do it. And now I'm going to look at the prompt output, and we are going to compare it. So let us say classify each as either vodka or use this particular text, and let us see how this works. So we are going to take this text, go down in the test prompt. We are going to use the new test that we have given, and we are going to look at the output. So test, that's going to create a problem. New prompt. I'm going to say test prompt. We are going to give the new prompt here, and we are going to give the trained model. That's very important. We have to give the trained model out, and we are going to print it out. So that, let us see how's the output. So the response is very similar to how the earlier GPT used to give. So let us try that also. So let us see what the earlier GPT provides, the regular GPT. So in case of the new data that you have provided, the output between the earlier GPT and the fine-tuned GPT is not very different. This is because the data set that we have fine-tuned is very minimal, and we have fine-tuned it only for 5 epochs. When you have a huge data set and when you are going to train it for even 3 or 4 epochs, it is usually sufficient. But when you are going to use it for a lesser number of epochs with lesser number of data set, your model will not be able to learn properly. Also, you can see that in the validation loss also. So the training loss has continuously reduced. It has become very low, but the validation loss is horrible. It's almost 3.64. So basically the model has not learned a lot. In fact, the validation loss has started at 2.5 and it has increased. So basically these are the challenges that you will face. And why I am sharing these things and showing you something that is breaking, because it is pretty normal. You will see there are things, you will see such kind of issues when you are training, and you have to come out of that by modifying and learning from the problem. If I actually show you something that is already working, you are not going to learn anything out of it. You have to see what is failing, and then you need to find out how it is solved and then move forward. So that is one of the important point I wanted to share here. Also, as I was trying to explain to you, that if I have to use lesser GB, so what will I do? How to train in a lesser with a lesser GPU memory? So in case if I use, instead of using 8, if I use 2, and if I am going to say I'm going to maintain everything else same, okay, and I'm going to modify the training args, and I'm going to modify the trainer because the args is modified. And now if I'm going to train, you will see the memory that I am using is very low. So earlier it was using 11 GB, but in order to do the training, now it is using just 5 GB. So the batch size that you use is very, very important. If you use a huge batch size, then the memory that is required for the evaluator as well as for the optimizer becomes bigger. Because of that, the GPU memory required is also bigger. So this is one of the ways you can reduce the memory required for training. The another way that you can use for reducing the memory is by using the PEFT adapters, and also by quantizing the model. These things I will discuss in the next video, where we discuss with the testing Gemma notebook. But for this video, I suppose that you understood the entire process of how to fine tune and what are the various errors you will face, and how to especially process the message. So this is very, very important. Now you have to process the message properly and then send it to the model. And also you saw that how to work with the batch set, what are the epochs, the batches, the steps, how to save it, how to load the save model, and do the testing. We saw a lot of those stuff. And also do take a look at this particular Transformers universe to get more idea on what are the models, how to work with the tokenizers, and how to look at the various existing tasks. So you can take a look at all these things. I believe that you have learned a lot from this discussion. It's a long video. Do look at the video time to time again, so that you will get more idea. And if some of the points I have missed it, do let me know through the comments. I'll be able to help you out. And finally, do subscribe to my channel for further kinds of updates on similar topics. With that said, I would like to leave the video with 4 words, that is fine tune, explore, explore. See you guys. Have a great time.